All right, looks like we're live.
Yeah.
Namaste, everyone. Welcome to the Cārvāka podcast. This is your host, Kushalmehra, as usual, welcoming you to another interesting discussion. This one is unique because if you guys are regular viewers of our podcast, you know that I always try to bring in, more and more scientists and try to have discussions about subjects related to science and latest discoveries that are happening in India or are done by Indians across the globe. I've spoken to Anand Raghunathan, I've spoken to Dr. Karanjani, and Alok and Ronajoy too recently. So in the continuing tradition of me trying to get amazing scientists and giving the platform to whom I believe are the real heroes of India, I'm very happy to welcome Dr. Gobardhan Das. Dr. Das, welcome to the podcast.
Thank you. Thank you.
So, Dr. Das, let's start with this. I'll request you to, tell the viewers and the listeners who are going to listen to the audio version later on a bit about yourself and the background and what kind of a work have you been involved in over these years.
Let me talk about my little background. I'm coming from a very small village of West Bengal in Bardhaman district, and I'm coming from a very poor family. And then over a period of time, I thought we have to do something for the society. So basically, then my education. I don't want to go in length, but I did my bachelor's in chemistry honors and then biotechnology, PhD, and then I was in US for around 12 years, and in US I was at Yale Medical School, and then I was heading a immunology lab in one of the world's leading pharmaceutical company, Aventis Pharmaceuticals, and then I came back to India. Why I came back to India, because when I was visiting India from US, my father told me that jungle में मोर नाचते तो कौन देखता है. So I thought that one of the turning point of my life, and then I gone back to US, and within 6 months I came back. I thought I have to do something for the country. So when I came back to the country, and I was really looking for, with my expertise, what I can best contribute to the country. As you know, the tuberculosis is the biggest problem in the country. Every 3 minutes, there is a person dying out of tuberculosis in India. So, and coming from the very countryside, remote village, I saw the people are suffering, and I thought I should chip in there, and I should use my knowledge and the expertise if I can find something which can actually help the community, the our Indian community. So that is what I started tuberculosis research.
All right, so Dr. Das, let's start with this because obviously there have been a series of papers when it comes to your breakthroughs and the research work when it involves tuberculosis. So can you take us through the journey itself? So how did you guys conceptualize? So let's say how did you guys hypothesize is the right word. So when you look at a problem like tuberculosis, so what were the areas that you felt in terms of? I want to get onto the current paper which was related to Curcumin, but before that, I wanted to understand your journey because it's obviously not a one particular journey like which has led to this current breakthrough. So what have been the steps that have been involved in this particular research that you have been involved with many others when it comes to the treatment of tuberculosis or latest breakthroughs when it comes to the treatment of tuberculosis?
Okay, so let me tell you two things. So when I was looking at this tuberculosis, when I decided to rather work on tuberculosis, what we found there's a big problem in tuberculosis. One problem is, although we have drugs, treatment, the treatment is for 6 months, which is called minimum 6 months, which is for regular TB, and for drug-resistant TB is the 12 month, 18 month, depending on the what kind of drug resistance it is. If you look at other infectious disease, the antibiotic treatment is at the most 3 days to at the most 2 weeks. So why we need to have this 6 month treatment? The my in our native mind struck on this issue. And then when we looked at, I'll come back to the research in a little later. The second thing, what the point struck in our mind, the vaccine we have, which is called BCG, which is given to everybody, and that BCG really doesn't work, at least in adult pulmonary TB. And this BCG is discovered in 1921, almost a century ago. So this BCG is not working. Still, we keep on taking BCG. So thereafter, there are many clinical trials being done with many other candidate vaccine, but so far there is no success. So we thought we should chip in a little different way, so that we should go out of box thinking and non-conventional way if we can design a vaccine. So that is what the two things we started working on, and so that is what we chipped in tuberculosis research.
All right, so just for I'm sure nobody would actually not even know. So you just mentioned that the BCG vaccine does not work when it comes to treatment of tuberculosis in adults. Now, could you actually elaborate the problems from a scientific or a medical point of view? Why don't they work? Because I'm sure nobody would even know that why, A, they don't work, and if they don't work, B, why don't they work? I mean, what could be the potential problems?
Well, I mean, so then I'll go back one step back. When we started work, then only knowledge that was known that BCG really doesn't work for adult pulmonary TB, and nobody knew why is really it doesn't work. And the then vaccine research, TB vaccine research, continued to discovering new candidate vaccines and testing it, and many clinical trials done, but none of them are successful. So then our first question we asked, the why BCG really doesn't work, number one. And number two, if can we modify BCG, or if we can add something on top of BCG so that BCG can work. So coming back to your question, BCG doesn't work. In our discovery, what we found, if I can enter in a little technical term, there is one type of our immune cell is called T cells. As you know, T cells are being killed in HIV infection and so on and so forth. So there are the T cell subtypes. There are several. The two of the subsets, namely we call it Th1, one type, and the Th17, the another type. These are the two important subtypes of T cells are really required for optimum vaccine efficacy against tuberculosis. First, we discovered that. Then we discovered that BCG can mount only one type of the T cells, which is Th1. But it really cannot mount the other type of T cells I was talking about, Th17, they cannot mount it. So therefore, to have a optimum vaccine efficacy, we need both Th1 and Th17, but BCG can make only Th1. Now the research become in India and in abroad, there are many people started following us and our research, and then people are trying to make a recombinant BCG where we can make actually to make both Th1 and Th17 so that we can get better vaccine. So we are also doing that, and we have some lead. In addition, you are being a scientist, you have to find out, little smarter way. What we tried to do is, already BCG is approved vaccine candidate. People are taking. And can we add something along with BCG, which is also either we are regularly taking or approved drug, so that BCG started making, instead of only one type of T cell, we started making both type of T cells. So we started starting from the all natural compounds. One of the natural compounds we found, which is curcumin, is nothing but it's coming from the turmeric. We use all turmeric in our everyday life, right? But its compound is curcumin, is active compound, and even if we eat this curcumin, generally it doesn't absorb. So goes away. So it really doesn't make any difference. So what we did is that we engineered this curcumin in such a way that the absorption is much higher, at least 50 to 100 times higher. And if we, along with the BCG, along with the BCG, we saw all of a sudden dramatic result. So we saw this is vaccine efficacy goes 100 times better. So that is what, and followed up the many other compounds, we found it out. We are trying to even make better, which is along with BCG, if we can give them this small compound curcumin, later on we found the clofazimine, the vaccine efficacy actually improves 100 times to the 1,000 times. So this is a very success, and so far we have done in the animal models. As you know, one cannot directly go to the human. We have to test with several animal models. In animal models, we are successful, and we are requesting Indian government to take it to the next step or give us the fund to go to the next step. So we have already done in small animals. Now we would like to do like animals like monkey, and then finally we can go to human. So that is what one of the research we are doing. And if I can go to the little technical term, this is, as you know, vaccine efficacy mostly depends on this T type of T cells, but they have to go to in the memory. As you know, we are injecting today, we are expecting to protection in down the road in 30 years later. So that is what. So we are now engineering how this memory response, this two-stage memory response can be engineered for a long-lasting memory. So once the children is injected or vaccinated with this kind of formulation, they should be protected for the lifetime.
That sounds very interesting. So I just had one more question in regarding to the Curcumin work.
Right.
So what would be the usual time period that must have taken you guys to come up with this hypothesis? Because that it's just something that fascinates me, and I'm always interested in knowing, how does a person's mind work? So why Curcumin? What fascinated you about that particular that particular, to use a correct Sanskrit term, padarth? What was that? What was so fascinating about that padarth that you were like, no, there's something out there, and we need to work in this particular padarth, and let's see how it works out. So what was the time frame, and what went on behind? I just wanted to know the behind the scenes, because that sounds very fascinating to me.
Yeah, yeah. Okay. I mean, in this regard, myself or Anand spend hours and hours after hours, days after days on coffee table. Let me tell you, I mean, how we came up with the curcumin. So first, our discovery was we need this type of T cells that we are talking about, right? And then we saw another subsequent paper we published, and we saw this is, well, for optimum vaccine efficacy. I said the memory response. There are one. I'm sorry, I'm entering in another little technical term. One is called central memory. Those who live for long, long time. Another type of memory, which is the immediately called immediate memory, which is called effector memory. It's not a very difficult term though. So now what we saw is the central memory cells are required but is not being produced by BCG. So then, but we have sufficient of effector memory cells. Now in our mind, we wanted to make these effector memory cells or switch effector memory cells to the central memory cell. If we are successful, that will give a long-term protection. Now, how do we target that? So over a period of time, literature and our own data, we are trying to find out what is the really gene level, the difference between these effector memory cells versus the central memory cells. After many discussions and then literature and digging our own data, we found one very interesting molecule, which is called KB1.3, potassium channel. As you know, that the cell exchanges ion, etc., potassium ion, sodium ion. So one of this potassium ion channel we call that is voltage gated, KB1.3. You don't have to remember the name, but the name of this channel is KB1.3. Is predominantly expressed on the effector memory cells. So now the argument is, if we can inhibit the effector memory cells, can we make more of the central memory cells? Because immune system works always in balance. If it is 100, somebody is 10 and somebody has to be 90, and vice versa. So if you can inhibit the 90, can we make other one is the if you can inhibit this 90, can we make other one 90? So that is the concept. Then we started looking, what could be the inhibitor for this target? Then we started searching. And then one of our old data was, this molecule actually binds to this target. Then the simple one experiment we asked, can you see if you can put KB1.3 inhibitor, can we switch from effector memory to the central memory? And indeed it did. Then we saw, Curcumin, the structure, it may have some affinity to this target. Another kind of experiment immediately we did it, and indeed it does. And then next question was, then every time we are taking the curcumin, but why not we are being protected? Then the thing is, literature says that curcumin doesn't absorb in the system. Then we had to go and re-engineer the curcumin. So that is the kind of pathway we did. Searching pathway or brainstorming we did. So later on, when we are trying to extrapolate even better efficacy, we are trying to search even better inhibitor. Then we found another one, which is called clofazimine. Clofazimine also binds to the same target, and clofazimine is already being used for some other ailments like leprosy. So we did the simply BCG plus clofazimine or BCG plus curcumin. Gives a fantastic efficacy for tuberculosis vaccination. And I'm talking about so far we did in animal models. We don't have funds for, or we didn't, so far we haven't done for human trial or monkey models so far. Yeah.
So, I remember reading, I think it was the Telegraph article, if I remember correctly. And, it had, actually, I have the quote right in front of me. So the quote stood out to me. That's why, I wanted to share this quote with the audiences and also ask you the technical reasons for this. So some anonymous reviewer had written that this study challenges established dogma and convincingly demonstrates that while macrophages are the natural host for replicating bacteria, mesenchymal stem cells are the natural host for dormant bacilli. Now, can you explain this? Because when I read this, I was keen myself to understand what is this established dogma and how have you guys changed the established dogma and what are the treatments now?
Okay. So you're talking about two different groups. Well,
Yeah, yeah, I know.
I do. So this is I'm now this is vaccine part. I'm coming to the therapy part. This is the other paper actually. The
Yeah, yeah.
recent.
I'm talking about two papers, Suvik. Yeah, yeah,
Yeah. So basically, this is the other paper.
yeah.
Okay. So in TB therapy, as we know, I said this is a 6 month treatment, and if anybody withdraw before 6 months, that TB gets reactivated. So first we started looking at the kinetics of this. Our question is why we did 6 months. In other infectious disease, it takes only not more than 10 days. So why in TB takes 6 months? But when we looked at the kinetics of bacterial clearance, you'll be surprised to know within 3 to 4 weeks of treatment, 99% bacteria disappear. Only 1% bacteria hang around, and they are the one takes another additional 4 to 5 months treatment. And why this 1% bacteria doesn't respond to the antibiotics? That was the question we were asking, and nobody knew. And we discovered before treatment, actually, MTB is in two places. One is in macrophage, which is historically known. MTB infects in macrophage. Nobody knew MTB infects any other cells. So when we did experiment, what we saw is upon treatment with antibiotics, almost all of the bacteria which is in macrophage are cleared off. But the less than 1% bacteria which is hanging around in other cell type, we discovered that is in mesenchymal stem cells, they do not respond to the conventional antibiotics. So that is the first discovery. Then we did series of experiments. What we found, most fascinating thing is, in less than 1% bacteria can infect this mesenchymal stem cells, and upon infection in mesenchymal stem cells, they simply hide and they become dormant, this hibernate. If I in a simple language is just simply go for hibernation. Say do not metabolically active, they do not replicate, they simply go and sleeping there. Then we started working on why they are sleeping there. Then we found out once this stem cell, these stem cells are infected by this TB bug, they simply hijack the stem cell. After hijacking, they say they ask the stem cell to synthesize lipid. We all know lipid, the fat molecule, fat.
Yes, fat molecules, lipid
Or
cells.
lipid cell, lipid. So once the lipid is ready, they go and hide inside the lipid. So as you know, within the cell, there are many other organelles. Within the cell, there are many other compartments. They are made up of lipid. So now the cell start thinking, this is our own organelle, own body part. So they do not kill it. And the bacteria, TB bacteria, sleeps in there happily, sleep in there. When they sleep in there, so basically no antibiotics actually can kill them. And those hang around for 4 to 6 months. Even after 6 months, there are many patients they get back the disease. So that is what we call latent bug or dormant bug. So now the theory comes in. For the successful treatment, you have to kill not only bacteria which is hiding in the macrophage, but also bacteria you have to clear from the stem cells. Then we started talking, how we can really clear these bugs, and few of the methods we already elaborated. So here, so that is what is changes the central dogma this way. So far, people knew, historically, people knew macrophage infects the TB. True. But the macrophage also infects the stem cells, other type of bacteria that's never been known. And this actually rewrites the TB biology or the treatment biology of tuberculosis.
All
And
right, sir. So I have to ask you this question because usually, I mean, this is my experience of how, as an outside observer who's keen about science and work in science, is that whenever there is a latest discovery which, in a way, challenges the standard way of looking at things, or in science, I know it. The word sounds very weird, but even in science, there is something called the orthodoxy and there is something called the heterodoxy, right? So in this very sense, I think the your discoveries and the two papers that we have discussed till now, especially this particular paper, actually kind of changes the fundamental way of looking at how tuberculosis spreads or works in a particular way. So how has been the response for your work and your discovery, as far as you and Anand and the entire team are concerned, from within the scientific community as of now?
well, I mean, scientific community, when we are proposing these, as you know, the any dogma, when you try to change, there are a lot of questions. It took almost 4 years, 5 years to really convince that with many experiments. That is, in fact, we had to convince ourselves first, and then had to convince the scientific community. And then finally, when the paper is accepted, it's now accepted in the scientific community. Now, what I can tell you, after our discovery, I know there are at least 7 to 8 different groups within India are working on this stem cell thing. And also, I know there are many groups started working on stem cell. In fact, that there is already there is a clinical trial going on in Sweden. So using these observations.
Yeah, that sounds fantastic. I mean, we rarely get to hear such news of I don't know how to put it, because anyways, as a country, I always feel that when it comes to news about science and discoveries that are made in India, we're anyways starved when it comes to things like these. And to even know that something that was discovered in India has now led to further research in the West too. Now it's so heartening to hear, to me as an Indian and someone who has deep interest in science and things that are related to science. So actually, I would like to congratulate you on that. But sir, I also wanted to understand this, that now, so when we were discussing we were having a chat offline, you had said that now you have reached a level when it comes to, over obviously not just these two papers, over the years of spending hours and hours on researching on tuberculosis and things that are related to tuberculosis, you've reached a level where we might have the final solution. So when do you think, in the future, in the ballpark range, do you think we will actually get to a stage where we might be hopefully having a final antidotes of sorts for people, people in our country, and we will be getting rid of this terrible disease? So when do you envisage these things to turn out, as they say?
See, this is so far we have done in animal model, and I don't know. Should I tell you the bitter truth, or I don't know. So one thing, see, I mean, for researcher we did research. For translation, there are it's a very different ball game, and I can tell you the overseas they are much more active, and I can tell you right now I am adjunct professor in UT Houston, which is in US, University of Texas in Houston. I'm adjunct professor in Shanghai University, China. have active collaboration and been right now. I'm also adjunct professor in UKZ in South Africa, and I was actually visiting professor in UTS Sydney, but I couldn't keep it UTS Sydney. But I'm working on this. So they are much more active. Actually, they want to pursue what we are doing and what our research and in fact, you might be knowing American Museum of Natural History made some kind of documentary of our research, so which is a rare, what do you call it? And rather, I am honored that they made it. In India, I don't know. I mean, if I'm given the chance, definitely we'll try our best to develop something. You know, hopefully, we can translate it soon. And these are not very difficult to translate. As you know, this is our discovery, almost like a repurposing. Giving the BCG and along with Curcumin. Curcumin is everybody uses Curcumin. In fact, the pills are available. And for this 6 month to 1 month, we are talking about the therapy. Uh, and if I can tell you in another simple term, all we are simply proposing, um, in addition to antibiotics, add some statin. Those, as you know, the blood pressure drug, the Lipitor or Crestor or this kind of drug. And this is already been used. There is no problem. We can easily go for the clinical trial. So that easy to do it. But whether we'll be able to do it or not, especially in India, that I really cannot answer this question to you. I'm sorry.
Yeah, and this is where I wanted to conclude our discussion, because as I told you, I have to ask you this question now. In my experience, we hardly have active research anyways going on in India. I mean, with you, Anand, and I'm sure there are many, but if I'm talking about in comparison to the global scale of active research that happens. So now you're a scientist who's actually involved in active research. You're as they say, you're someone who has his skin in the game. You're right there in the middle of it, searching, experimenting, hypothesizing, collecting data, testing it, replicating it, walking the walk, talking the talk, as they say. Now, we all know how things are in this country. I mean, we all love our country. Now, as someone, I mean, you started the discussion by saying, you wanted to, you came back, you wanted to do something, and you felt very strongly about tuberculosis. But then when you see how things are, so how do you and Anand, I mean, Anand is an eternal optimist, that I have to say. I mean, at least how Anand comes across to me whenever I talk to him. But so how do you stay positive in all of this and you still keep going at it, is something that I wanted to know from you too. And B, where do you think, I mean, the overall attitude, and this is not about the overall attitude towards science from the point of view of the state and our societal attitude towards science and scientists too. So where do you think we need to make our changes to make this more of a culture of curiosity and breakthroughs?
So once again, people may not like it if I, but I'm always straightforward. In society, including in government, we are very have a very good, very positive view about scientists, and they respect scientists. In fact, government actually respects scientists. Society respects scientists. But among the scientists, there are, I should say, three types of scientists you can see. One kind of scientist always you see is they are information hungry and kind of what want to do something for the knowledge. Another scientist, kinds of scientists we have it. I don't know the number. Please don't ask me the number. They are always award driven, right? Award driven. So basically, shortcut science. Basically, do some science and then try to get award. And some of the scientists that basically they do money making, basically. Do a patent, sell something. So I myself, what I think by because of my training and because of my father's, my bringing up, I try to. I work for basically for knowledge and if I can contribute something to the society. Why I am saying is I did PhD with a great person, Gan GC Mishra, was the director of NCSS Pune. He told me that there is nothing for shortcut. So basically, you have to go all the way, you know, you know, foolproof. Then I ended up going in the Yale Medical School. I worked with a person, Charles A. Jenner Jr., who is supposed to be the modern day. He is the father of modern immunology, actually. So he taught me this is how to tackle the problem and how to go in length, not the short term gain or something. And then finally, my training was in pharmaceutical industry. As I said, I work for Aventis Pharmaceuticals. So I see the things not in a terms of awards. I see things in the how I can really from a challenging question to come to the translation where I can really contribute to the society. I really don't want to, patent something and get some money and then forget it. And I don't want to do that actually. So that is what, if I can save one life in my whole life career, I think I'm successful. So that is what I'm trying to do. And I'm lucky that in the journey I got a good friend and the one of the rather best friend, Anand Raghunathan. We spend hours after hours, and both of us don't believe this all this patenting and small things. Rather, we would like to contribute to the society, either for the knowledge. On the basis of that knowledge, somebody else can chip in and do something good, or directly if we can translate to the something which is useful to the society.
So, Dr. Das, so I can't let you go without asking you this question too. So now, what's next? So can you tell us some what are the next steps that you guys? Are there any other exciting new areas you guys are working on together, or you yourself are working on, or
Yeah.
it's right now the focus is all on tuberculosis itself?
Well, I mean, see, the when we do something actually that already this is an open new field. When we did the TB, the many people are following up with the many other diseases. I can tell you, when we have done our work with the stem cell, and people started showing that in same thing happens in the leishmania. As you know, leishmania only they can find after the bone marrow tapping and etc. So I mean, these are being people are taking up. So basically, and the new exciting area. Then right now, okay, let me in two parts. Number one, we would like to translate this thing so that it can go to the society. For example, I said is a curcumin, I said is a clofazimine, and along with the BCG, if we can really want to do clinical trial. And also for this treatment, if we can shorten the treatment from 6 months to 1 month, that is also we would like to go for clinical trial. Yes, apart from this, there are a few more exciting things are going on in the lab, both my and Anand's lab. I can tell you, although I may not tell you the whole story, We know now from where the drug resistance is coming, the origination of drug resistance. As you know, this is whole world is now working on the drug resistance, and drug resistance is really a big problem, not only in India, in throughout the world, irrespective of socioeconomic status. So, with our discussion and the preliminary results, we know from where the drug resistance are being originated. So that if I can really find it out and that has been true, what we are thinking and what our data says, that will be another great story, I think. So,
That sounds like a lot of fun, Dr. Das. And you know what? As someone, again, as someone who's an admirer of who I think are the real heroes of India, and this is my view. People can call me biased, or whatever. I mean, I believe that in a culture like India, we tend to worship false gods. To use the word, Arun Shori's famous book, "Worshipping False Gods," were about something else. But I think scientists are the real heroes of our society. I believe that societies that respect scientists, follow science, have a rational way of looking at things, a real they follow these things, are societies that become great. I think when we were at the pinnacle of our civilizational peak, or when we were at our, I think we were doing those things, we were celebrating those. I think somewhere down the line, as a layman who's very passionate about this subject, I think it hurts me at times. And that's why I try, whatever little platform that I have here at the Cārvāka podcast, I try to talk to as many scientists as I can, because I think, to me, they are the real heroes of our society. Because I mean, your contribution to tuberculosis along with Anand, I think these are significant contributions. Because जैसे आपने कहा, you said even if I save one life, you'll be a happy man. But I know it will be more than one life when eventually these things come to fruition. So to everybody who's going to be who's watching this right now, or who's going to watch it later, or listen to this on the audio version. So I want to tell you guys that I have shared the link of the paper too. I would recommend read the papers too. Try and read the science. You may not get it, but guess what? If you don't get it, I've shared Dr. Das's Twitter handle too. Ask him those questions. I can guarantee you the best thing a scientist wants is somebody asking them scientific questions, and they'll be more than happy to answer it. The problem is nobody is asking them the scientific questions. So that's what, and scientists would love that to happen. So when you go to the description of the podcast, wherever you're going to watch this from, there's the link to the papers, there's the link to Dr. Das's Twitter handle. Please follow him, follow the work, share the work, encourage more of this work. When we create this atmosphere where not just my podcast, unfortunately right now I'm the only Indian podcast that actually calls scientists and talks to them. It's a shame. It's actually a damn shame that I'm the only one who does this. So I would request all of you, the listeners of my podcast, actually start telling other podcast hosts, tell them, call these scientists, talk to them. And Dr. Das, once again, from the bottom of my heart, really, thanks a lot for all the research that you've done along with Anand, and thanks a lot for coming on my podcast.
and thank you so much. And I would like to add 30 seconds here. Uh, Anybody is, even the simple question, we really appreciate it. That's because all the great science actually starts with a very simple question. In fact, our story also started with a very simple question. So, and everybody knew that treatment of TB takes 6 months. Other infectious disease treatment takes only 10 days, and everybody know that, but nobody asked the question why. And when asked the question why, there is now uh, found the reason. Now we can have the solution actually. So don't I will request all the viewers, all the people, those who are alive, ask your question anytime, and then that simple question may end up giving the big story, big solution. So no question is small question, and everything starts with the small, and it finally takes a big shape.
Awesome. So, guys, you know what? It's time to wrap things up. Once again, thanks a lot for listening to the podcast. I request you guys to subscribe to the channel, share it with as many people as you can. Also, I'm already there on Patreon. The link's on the screen. For the ones listening, the link is www.patreon.com/Cārvāka. So you can support me there. And, on that note, I would like to say namaste. And once again, thanks a lot, Dr. Das. Uh,
Namaste.
I'll
Yeah.
see you guys next time. Take care.
Thank you. Thanks for having me. Bye bye.